Hello, in this video we're going to talk a little bit more about the different coefficients of friction, static and kinetic, and after that we're going to do an example to put together everything we've learned in this section. So let's make a graph. We're going to graph friction force versus applied force for, say, a block sliding across a table. So vertical is friction and horizontal is applied. Alright, and if we did this, we would see that as we increase the applied force from 0, so again, we've got a little table, we've got a block, and we're pulling on it, comparing the applied force to the friction force. The friction force is going to start out as static friction, and so it's going to be exactly equal to the applied force up to some maximum value. And if we kept increasing our applied force, suddenly the block is going to start to slide, and then we'd be using kinetic friction. In that case, what happens is the friction force dives down, maybe 20-25%, depending on the materials. And then, I'm purposely drawing this a little bit wiggly, the friction force would be constant, at least more or less constant, and we'd have kinetic friction. Okay? In reality, there are little wiggles depending on the individual cold welds that are forming and breaking, depending on the larger scale roughness of the surfaces. If you've ever had two objects slide across each other and they squeaked or squealed, that's a manifestation of the slightly different values of the kinetic friction as it grips and those grips break. That causes squeaking or squealing and all kinds of other sounds as things move across each other. All right. But clearly we've got these two kinds of friction. Static friction, where the friction force is exactly the same as the applied force, so this line has slope 1. Or, well, has slope mu s, I guess we would say. And then we have kinetic friction, which... No, actually, I take that back. This line would have slope 1. The friction is exactly the same as the applied force. And then we have a constant kinetic force. So the important takeaway here is that the maximum value of the static friction is always going to be greater than the kinetic friction. In other words, it's easier to get an object to start sliding, it's harder to get an object to start sliding than it is to keep it sliding. It wouldn't make sense for this to be the other way around. It wouldn't make sense if it was harder to keep an object sliding than it was to get it sliding, because it would stop right away. And then effectively that would be, by definition, static friction. So this is the only thing that even makes any sense. Let's consider some typical values here, and this is just to give you a sense of what kind of numbers you should expect for these different mu's, different coefficients. Okay, so in general, mu, static or kinetic, is going to be less than or about 1. Okay, it could be larger than 1. It's not that 1 is some top value. You can have 1.1 or whatever. But usually these things are a little bit less than 1, down to, I don't know. Well, I can tell you that something that's slippery is less than or about 0.2. So anything you would call slippery has coefficients down at 0.2 or below. Things that you wouldn't call slippery are above that, approaching 1, sometimes a little bit bigger than 1. Okay, so let's try an example. Let me pause the video for a moment. I'm going to draw a little sketch and type up the problem, and I'll be right back. Alright, so in this problem we're going to have an inclined ramp at some angle theta. We'll have a block sitting on there, and there's friction between the ramp and the block. Let's say that the coefficient of static friction is 0.8, and the coefficient of kinetic friction is less, so it's 0.6. I'm just making up these numbers. The first part of the problem is what can be the largest value theta here that we could have without this block just sliding down on its own. So imagine we start with this tabletop flat, block sitting there, of course it would just stay still, and we slowly lift this up, tilting it more and more and more. At some point it's just going to slide down. Let's calculate what that angle is going to be. So at heart this is a force problem. So to solve a force problem we want to make a free body diagram. let's make a new sketch that will serve as our free body diagram. For reference, let's add the ramp and the block to this sketch. Those aren't technically part of our free body diagram, but they help line things up. So we're going to treat this block as just a point, and we're going to draw the forces that act on it. There are three forces acting on this block. There's gravity, which pulls straight down, and that's going to have magnitude mg, where m is the mass of the block. We're going to have a normal force, which stops the block from falling straight through this ramp. The normal force is always perpendicular to the surface. And the third force is friction. If we're looking for the maximum value without the block sliding, then this is going to be a static friction because the block is not sliding. Not only that, but since we're right at the maximum without it sliding, the static friction is going to be at its maximum value. And the maximum value is the coefficient of static friction times the normal force. Alright, so those are our three vectors. Now we want to pick a coordinate system. This is an inclined problem, so we want to pick a tilted coordinate system that matches our ramp. X, we'll say, is the direction along the ramp, and y is the direction perpendicular to the ramp. Which means that we need to break up this vector here, mg, into its two components, a component in the x and a component in the y. So we need components like so. This angle theta shows up here. Okay, so like I said before, it's something you should figure out at least once, but as it turns out, when you tilt a ramp like this, theta is always the angle that shows up here at the top. Okay, so let's write down an equation, or two equations actually, one for the x direction and one for the y direction. And in both directions, the net force is 0 because the block is not going to be accelerating. In fact, it's not even moving. Okay, so in the x direction, in the positive direction, we're going to have the static friction force. In the negative x direction, we've got this component of gravity, so that's mg times sine theta. And altogether, they give us the net force, which is 0. Now we can make a substitution because we know that the static friction force is equal to mu s times the normal force minus mg sine theta is equal to 0. Okay, now this is not enough by itself. We can try and solve for theta, but we're not going to get too much further. We can move mg sine theta to the other side of our equation. That would be equal to mu s times the normal force. Divide both sides by mg, and that's the furthest we can get because we don't yet know what the normal force is. The normal force is not mg. They're not in opposite directions. The normal force is actually less than mg. Okay, and we figure out what it is by looking at the y direction. So in the y direction, upward we have the normal force, and downward we have mg times cosine theta. That's this component of gravity. Those are the only forces in those directions, or in that direction. The net force in the y direction has to be 0. So that tells us what the normal force is. The normal force is equal to mg times cosine theta. Great. So now we can plug that in to our first equation. Let's do that on the next slide. So we have sine theta is equal to mu s times the normal force divided by mg. That's just what we had in the last slide. And we're going to plug in the fact that that the normal force is equal to mg cosine theta. Okay, so plugging that in, we've got sine theta is equal to mu s on mg times cosine theta. M and g cancel out. So it looks like the mass of the block is not going to show up in our answer. In fact, that's true. It doesn't matter how massive the block is. All that really matters is the coefficient of static friction and how much we've tilted our ramp. So we need to get the thetas all on one side of the equation to finish this off. So we'll divide both sides by cosine theta. And sine divided by cosine is tangent. So tangent theta is equal to the coefficient of static friction. Therefore, theta is the inverse tangent of the coefficient of static friction. Okay, now that's kind of a specific result for this specific problem, so I wouldn't quite put this on your equation sheet. But still, it's interesting, I think, that so little shows up in the final answer, that it's actually all determined by the coefficient. We were given some numbers here, so we can get a number for our answer. On the previous slide, we had the coefficient of static friction was 0.8, and the inverse tangent of 0.8 is approximately 38.7 degrees. Okay. Now, let's do a follow-up question. We'll put that over here. Question is, what will the acceleration of the block be? So we'll assume that we keep theta at the same angle. Okay, and the tiniest disturbance would make this block start sliding, and once it is sliding, it's going to keep sliding, because the coefficient of kinetic friction is less than the coefficient of static friction. In fact, that means it's not going to just be sliding at constant velocity, it's going to be speeding up, it's going to accelerate. So if we drew a free body diagram, here we've got the ramp in our block, and this is just to line up the vectors. We still have mg directed down, we'd have normal force perpendicular to the ramp, and we have kinetic friction. Okay? And then like last time, we'd want to break up our force of gravity into a component perpendicular to the ramp and a component parallel to the ramp. In other words, using a tilted coordinate system. And we're going to have a block that's sliding down this ramp. And so acceleration is directed down the ramp. Acceleration is in the negative x direction. So let's write down the x equation, and that'll solve for acceleration. So the x equation says that in the positive direction, we have the kinetic friction force, and in the negative direction, we have mg times sine theta. That's this component of gravity. And altogether, that's the net force in the x direction, which isn't 0 this time, but is instead equal to ma. Now it's up to you whether you'd rather say positive ma and then let a be a negative number. It needs to be negative because we're going down the ramp, or you could explicitly put in the minus sign and then you'll get a as a magnitude, as a positive number. Let's just leave it like it is, and we better get a minus sign when we're done. Okay? So we'll do a quick substitution here. The kinetic friction force is equal to the coefficient of kinetic friction times the normal force. Subtract from that mg sine theta, and that's equal to ma. Okay, well, what is the normal force? We figured this out earlier. It's right up here. So the way you would get that if we were starting fresh, just as a reminder, is you would look at the y direction of your y equation. So you just have these two forces. You've got normal force up, which is equal to mg cosine theta. So the normal force is equal to mg cosine theta. Okay, so let's continue this on the next slide. We're just going to write down this result. So we have mu k times the normal force, and we said the normal force was equal to mg cosine theta. And then we subtract from that mg sine theta, and all of that together is equal to the net force ma, where I'm expecting to get a negative number for a. Okay. Note every term has mass in it, so just like in the first part of the problem, the mass of the block doesn't matter. It cancels out. Because the mass of the block determines both the force that's pulling the block down the ramp, it determines gravity, and it determines the friction force which opposes gravity. So physically that's why it's going to cancel out. And the acceleration is equal to, well, every term has a g in it, so let's pull that out. Then we have a coefficient of kinetic friction times cosine theta minus sine theta. So it's not pretty, but it's not quite little g either. It's little g minus some stuff. Okay, and stuff that had better be negative. And don't worry, it will be. So if we put in our values, we'll get 9.8 meters per second squared. We said that the coefficient of kinetic friction was 0.6. That's just something we made up for this problem. Times cosine of theta, we're going to use that critical angle of 38.7 degrees, and then subtract from that sine of 38.7 degrees. And that's going to end up giving you negative 15.3 meters per second squared. And so as expected, the acceleration is less than 0 because it needs to be directed down the ramp. Alright, so that'll do it for this section. See you in the next section.